Donovan.
Good morning.
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 We put our phones up.
Hey, where are the phones? How many times I have to tell you? Damn kids.
What's poppin', Patterson?
Hey, how you doing, young primo?
Yeah,
Are you
ugly,
recording
bro.
a lot? You have a lot of new hits coming out? I haven't checked your channel lately.
I got 2 songs coming out on Friday.
Now we're talking.
Damn right.
Hey, let's watch our language. This is being recorded.
It is.
Oh, you just woke up.
I said, baby, what's the move?
Shut up.
Damn.
Okay, I'm almost in.
Frank.
What? God has shown up.
I think I have to turn down the audio or it's gonna. Okay. Who's that? The hoodless person there.
Connor.
Okay. Hey, Matt. So what I got to do is I got to take roll. So let's see. So I'm writing it down. Connor's here. Ethan's here. Jacob. Gael. Some of you don't have you don't have cameras. What's that?
They probably.
You got those turned off? You don't want me to see your beautiful faces? Good morning, Frank. Cameron. Will. Hey, I haven't seen some of you in 3 weeks.
Will, don't fall off your chair again.
Moted.
Will, you fell off your chair?
Yeah.
Xavier. Danila, have you recovered? Weren't you sick, Danila?
What?
Weren't you sick?
No, I just said that 'cause I didn't want to do the homework.
Okay, well, there you go. Okay, go back to Fortnite.
I'm playing.
Right.
Are you playing right now? Are you winning? How many points you got? How many kills this morning? Who the hell's up at this hour to play with?
Damn, man.
Zach? I can't see you.
Yeah, it's like 10 questions.
Gian? Charlie? Charlie, you have a skateboard circle in your room there? Going around and round on the circle?
Yeah.
Yeah, okay. So nobody appreciates my humor. I just want to point out. Jaden.
I do. What you mean, man?
Jaden. I liked your pineapple, man. Okay, Andrew. We don't get to see you? No picture for Andrew?
No.
Damn right.
Damn right.
And Nick
Nick is here.
and Leo.
Mm-hmm.
Leo's already been spending time with me. So is Cameron.
What?
On Zoom. Hey, it's a family show.
Oh,
Okay, Kieran. I think Kieran just has his name up there. I think he's eating breakfast somewhere else. Okay, let's see. Do I have everybody?
Forgot me.
I'm missing Luis and Catherine.
Yeah, are they on here?
I don't think so. No.
But Mr. Patterson, did you get me?
Hey,
Who
Mr.
is you?
Ray.
Ray, I did see you at one point. Ray, I see you on this computer. Thank you, Ray.
Did you get me?
Who's me? Matt.
Yeah,
No, I
me.
didn't. Thank you.
Did you get me?
Who's me?
Yeah.
Gavin, I didn't get you either.
Damn right.
Damn right.
End the show, Matt. Come on.
Okay.
Sarah missed
So
it.
let me see. I'm going to manage the participants. Right now I got 27. So I think that includes me. There are 2 of me. So 1, 2, 3, 4, 5, 6, 7.
I only see one of you.
Yeah, 4, 5, 6, 7, 8, 9,
Obviously.
10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay. Hey, if anybody knew, oops, somebody dropped. We went down to 27. Somebody's already left. They don't know how bad this is going to be, and they've already left. Oh my God. Look at that smiling face. Okay. Oop.
Obviously came with a love zone, man. That's good, man.
Here we go.
Yo, what the?
What the heck?
What just happened?
What the fuck?
Whoa.
Whoa,
Watch the language. I'm
What
turning
is
this tape. I'm turning this tape over to the dean's office. Okay. While I can share this, it won't go to full screen for some reason. So there you go. Okay, boys and boys, can you see that?
Yeah.
Yeah.
Sure.
So we're going to start with resources for our distance learning here. And so the 3 important ones are Google Classroom, where you get the assignments and turn in the assignments. And then there's learning resources on the website. So that's a page on the website that has the calendar for these days that we're in distance learning, which I'd bet are probably the rest of the semester, but that's just my guess.
Probably right.
And then we have the calculation videos page on the website and the homework page on the website. Okay. Any questions?
Nope.
Liars. So let me see. I want to go to a different share screen. Okay, so.
You know how to do that?
Well, I'm doing it. What I'm trying to figure out is which one of these. This might be it. Okay, let me try this.
Oh.
So are you having private chats while I talk?
I don't know what you're talking about.
Come on.
Hey, we can do that.
We would never do that.
Oh, come on. Edgar, is that you? I don't think I have you on my list.
His mic doesn't work.
That's okay. Okay, I put you on my list, brother. Now, here we are on the Google Classroom. And I know you know this, but you can't really do anything here.
Scurry.
Okay, if you go to the classwork page, then it lays out the assignments like what you see there. And you can see their due dates. Okay? So a few of you have actually done some of the ones that were due on March 10th.
Few of us.
Yeah. Hey, you're on an extended break. And it's tough to find time, especially with all those video hours you're logging. Okay. Then I put up some, people have asked me for makeup assignments, so there are some here, right? Grading period's supposed to be over Friday, so good luck. Okay,
Notice.
so anyway, this is a good place to get the assignments right there. And then turn them in here too. Okay? Okay,
Mr. Patterson.
yes, thank you, a question.
So when you posted the 4, 3, and 7 branch isomers, only
Yes.
one of them had a sheet.
Oh, is that true?
Yeah,
Okay, I'll go
So-
back and look. I might have to redo those then.
because only number 7 has a sheet.
Okay, thanks. Okay, thank you for that. Sorry about it.
No problem.
Okay,
You should be sorry.
Whoa.
right,
Whoa.
I should. Okay, give me a second. The tears are about to start. But anyway. You rang? Okay, anyway, if we go to the website, here we go. And we go to Learning Resources page.
Oh, wow.
Okay, so on this page is the document that has all the distant learning stuff on it.
Oh, wow.
Yes, this is an exciting opportunity for you. I admit it. Okay, so then I've got this here. You can see I've got office hours, right? Office hours coming up this afternoon, tomorrow afternoon, right? I still have to make the triple point document, which is the next document you're going to do. Okay. And then I have all of the previous 2 weeks stuff on here too. Okay. So is that clear? Where do we find that?
On the
your
learning
website.
on your website.
On my website someplace. It's on the
Learning resources on your
resource
website.
page.
Let's do it.
Damn right. Okay. So then I want to go here. I'm back on the website. You see that? And now I want to go to calculation videos. Okay, and so I've loaded some videos here and I'll put some more. Okay, so it should be pretty easy to get some of these done, especially for you laggards. Those of you who have been so sick that you haven't been able to do anything. Hey, Danilo, where are you going? I can barely see you. Okay, thank you. Okay,
Oh, my bad.
and then there's always the homework page too. Okay, then let me see what else I was going to tell you about here. Then you can always email me, and you can visit the homework page on the website. I've got some things there too. Okay, so do you know how to communicate, how to turn in your stuff?
Yeah.
Lucas, I have you already. You're already on here. Cameron, you look like you're in a hospital bed. Okay. Thanks for the hat, Primo. Now, let's go back. Oh, let's go to the next thing we're going to do. Okay, so this week is a 62 question Google form is the first assignment. The second assignment I haven't made yet. And the second assignment is on triple points and phase diagrams. Okay, so it took me a long time to make the Google form because I've got little videos in there and I've got pictures, right? And so, you know, most of the answers are all the above. So that isn't the point. The point is for you to get down the knowledge in that document. And the document's broke up into 3 parts. The first part has to do with boiling point. And so it's kind of like that first document we had last week, right? So the first document last week, you had to graph the boiling points for the hydrocarbons, right? And you had to watch a video on what is boiling, and then you had to say, well, how come the boiling point of helium is you know, I don't know what it is, 468 degrees lower than water. And then it talked about the fractionating tower, right? Okay, so that was the first, and a little bit, they had a little bit there in that document. Also, you watched the video on London forces. So the intermolecular forces that hold the molecules together in the liquid phase. Okay, so part 1 of this review that you're gonna do is on that. And I went over that yesterday during 4th period. So what I'm gonna do is post, if you need questions on how to answer those questions or don't really understand, I'm gonna post the Zoom class that we did yesterday in 4th period for part number 1. You with me?
Yes.
Today, we're gonna work on part number 2, and this is kind of a review, and maybe for some of you, it's your introduction to what document number 2 last week was about. And that has to do with the concept of phase change. And so here, molecular kinetic energy, the Maxwell-Boltzmann distribution, the mean free path of the molecule, and molecular confinement in a liquid. So that's intermolecular forces operate in close angstrom distances. There's enormous molecular populations, even in the smallest of drops. And the external pressure of atmospheric pressure works to hold all these molecules together in a liquid. Okay? So that was the whole point of the second document, and that's what we're going to review today. And then there's a part 3. And I don't think I have the part 3 slide on here, but part 3 deals with intermolecular forces. Okay? And with that, we went over that last Friday in office hours. So I'm trying to edit that video, and then I'll post that. So it'll be today's class, last Friday, and then yesterday's 4th period class, if you need help answering any of the other parts. You understand that? So I'll post those videos, and you can look at what was said about those things in that class. Basically, I do most of the talking. Okay, so does everybody understand that? On Friday, boys and boys, I should have the second assignment up. Takes me a little while to build these assignments. I'll have the second assignment up, and it'll be long, and then I'll go over that with 5th period on Friday, and then post their video if you need help with that assignment. Okay? What do you think? Do you understand what I'm doing?
Yep.
Okay. And so so I've got it broken up into 4 different things, and we might need a second one on the triple point. So maybe it'll be you guys again on Monday. Will be the second part of that triple point. Okay? So even though you only have 1 hour class and you really only have to attend that, you can also look at the videos from these other things to learn how to do these things. Okay? And then I've also got a video on like branch chain isomers number 7. And so I could put that up. If you still haven't done that, you could copy the answers right off of that and turn it in. Okay? Okay. So, you know, for those of you who haven't been doing much, now's a good time to get something done. And, you know, basically you just got to get this stuff turned in. That's why I have those videos already on the video page to help you out. Primo, your response means the world to me. Okay. Now, so today we're talking about part number 2. right? Okay, so in part number 2, we're dealing with the concept of phase change. So everybody knows what phase change is. Phase change is the same thing as state. A phase is a state. The reason we call it a phase is there's usually there's an interface implied. So there's solid and liquid at the same time. There's solid, liquid, and gas, or there's liquid and gas. So there's an interface where the gas and the liquid are, or where the solid and the liquid are, or where the solid and the gas are. And so that's, I think, how the name phase came about. But basically, it's a state. Okay? And the other idea of this phase is that molecules are moving from liquid to gas and then back from gas to liquid. So they're evaporating and condensing all the time. So it's kind of a dynamic motion going both directions. Okay? So in this one, of the 3 different topics about boiling point, this one is the most theoretical. So in this one, we look at the kinetic energy of molecules, and we get a little introduction to the Maxwell-Boltzmann distribution, and that's about probability. So basically, our concept of what happens with these molecules is influenced by statistics. And this started back in the 1860s when they started, because they took things like these bulk properties. You know, we measure a boiling point. Now we're going to say something about the structure, even though all we see is the temperature on the thermometer. So what they were trying to do back in the 1860s is they were trying to say, well, what's happening with the molecules and the atoms? And it was right about that time in the 1860s that they had a big science conference in Berlin. And pretty much everybody decided, okay, this idea of atoms has been around for 60, 70 years. We're all going to go with the idea of the atom now. That's going to be our concept. So they're trying to rationalize what they're saying about the atom, about molecules and their speed. So how is molecular speed connected to temperature is the big question that we spend most of the time on today. And then the mean free path of a molecule, that's how far a molecule has to travel before it hits another molecule, right? And so in liquids, they go very short distances, and in gases, they go distances that are about 500 times as far, okay? And then we hardly covered the last 3 topics, although those were in the document and they were in the previous little questionnaire. So that has to do with molecular confinement in a solid or liquid, how we keep the molecules together. It has to do with intermolecular forces that operate at very close distances, that there are enormous numbers of molecules, even in the tiniest of drops. And so all those molecules are holding the other molecules in there. Like it's like if you were in a scrum in rugby, you know, if you're in the inside, all those fat boys on the outside are keeping you on the inside. And that's how molecules work too. And then there's the external pressure. We went over some pressure things in part 1. If you watched that video yesterday, we talked about that. Okay. So anyway, that's a lot of talk. Let me switch gears. So the first thing we're going to talk about is the Maxwell-Boltzmann, and I hope I'm going to be able to find it here. Let's see. Did I find it? You know what? I hope I didn't kill that one. Okay, here we go. So, hey, right now, can you open up this document? And then we can just start doing the problems right now so that you can knock these problems out. And I'll just use these problems as a means of talking about the lesson. Wait, are you seeing what I'm seeing?
Nope.
Nope.
We're looking at the calculation videos.
I know.
Nope. Yeah, why didn't it change?
Oh, what?
I don't know why, because on my other screen, okay, let me stop. Okay, now, here I am. Ta-da. Now we're gonna share the screen. I'm so wonky with this thing. Are you with me? It says chemistry with MPATs. That isn't where I want to be. I want to be on this right here. Nope. That is not where I want to be.
Coronavirus.
Okay. That is not what I want. This. Do you see him?
Yeah.
Yes. Okay. So let's go. We're going to start at question number
Okay, how the hell do I get there?
20. Okay, do you know where to find this document?
Nope.
So you can get it on the homework page, or you can go to that coronavirus page on the learning, the learning resource page on the website, and it's also on Google Forms. So let's get to this document. So I'm also asking you to take notes like on this material. Primo, should we play some music while
Not on the
in this
website.
interlude here?
What type of music?
Your Primo song.
Well, I don't know. That last one had some naughty lyrics.
It's good.
Let
Bum,
Primo
bum,
get
bum,
off.
bum, 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 bum. Bum, 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 da-da-da. Okay. Is everybody on the document?
Nope.
No.
No.
62 questions. Oh my god. Yeah, I'm on it.
How many are on it?
I'm on it.
Where is it on Google Classroom?
Why don't you do the one that's on the homework page?
Is it the quiz?
That way you can do it more than once.
The Franklin.
Why would I do it more than once?
You don't want to do it more than once? Is that what you said? Since we're not having prayer this morning, I figure.
That's it.
Wait, isn't the fourth period class quiz?
Oh, I got that. You know what? I can't just play that. That won't work. Because I have the sound down.
Right.
Hey, you know what I'm going to do? I'm going to turn the sound down on this one. Maybe. Ah! Okay, well, that ain't going to work. How am I going to play these videos? How do I minimize my screen in this Zoom?
Top left. All right.
No, I don't have anything. Oh. And
Just
there
try to
I
play it.
What's up, Cameron?
Okay.
Oh, shoot.
Maybe I'll go, I'm going to try this. I'm going to try to take down. Can you hear me?
Pantera said F4.
Ah. Try Alt F4.
Man.
There is no F4 on the keyboard.
Are you retarded?
Ah,
F4 is not a
Are you actually retarded?
F4 is not a button. There's an F and a 4. There's no F4.
Yes.
Too close to the mic.
Are you on your iPad or phone?
I can't do it!
Wait, Mr. Patterson, I have a question.
Hey, you guys, you just want to call it Mr. Patterson?
No.
Okay, can you hear me?
No.
That isn't gonna work because there's an echo.
No, we can hear you.
Damn, there's hella echo.
What about now? Is there still an echo?
Yeah.
A little bit.
Still an echo?
Yeah.
It's because it plays out of the, let me just try
Kinda
something.
sick, though. I'll mess with it. Mess with
Hey,
it.
when does this class end?
10:50.
10:30? Oh, okay.
10:50.
50? 1050?
10:30.
50.
Are you sure?
Yes.
What?
Okay.
Schedule again. Just to make
Loaded.
load.
Wait,
Ooh.
Hey, what are you watching, Mr. Patterson?
who's on YouTube?
That's
Oh.
not working, huh?
No. Try changing the sound input.
No,
Like,
it's
go
not.
to the, like, sound thing.
Sound preferences.
Oh, I can hear it.
I can hear it.
I can hear it in, like, the background.
Hear it?
Does that work?
Yeah.
Oh, that's hella echoey.
It's good.
It's kind of rough.
Is it still echoey?
Yeah, very.
Okay, that may not work.
Wait, I'm fine with the echo.
I can't even hear it.
You can't even hear it?
Is this your favorite song, Mr. Patterson?
Now this morning prayer here.
Damn right.
Is the echo worse?
It's a little like
Now,
mic.
Hey, can you see that?
yeah.
Yeah.
Okay, so what do you notice?
Which one are you talking about? Like the particle one or the graph?
Okay, both.
Both.
The hella moving.
Okay, so what do you notice?
The
Moving.
particles are going at different speeds, at different time steps.
Okay, what do you mean different speeds and different time steps?
Like on the graph, it keeps changing as it goes. With like it's like 680 times step and then 740, 790. I'm thinking like the different speeds change as the time steps goes up or down.
Okay, and what is a time step?
I do not know.
Damn right. That's why you need me.
Yeah, can you tell
Just
me what it
sitting in
is?
those bedrooms, wondering what time steps are. You'd be nothing without me. So what is
Yeah.
a time step? I didn't actually look it up. What the hell? So what does the top picture have to do with the bottom picture?
Let's see. It's a top picture. I'm thinking that the frequency is what was I gonna say?
What does frequency mean?
It's like it's a vibration of sound.
Okay, that is that's a type of frequency. Frequency here means how often an event happens. Okay,
Okay.
so now let's look at the graph for a second. So you can see the line on the graph?
The like orange one.
Yes.
That one, yeah.
Okay, and then what about the time steps? Are they basically within that graph?
Like what do you mean with like in the graph or?
Yeah, so underneath the orange part, the time steps most of the time fit into that little graph, right?
Mostly yes.
Yes. It's not exact, but it's yes. Okay, so what do those time steps have to do with the little dots up above?
So like I guess the particles are always moving.
The particles are always moving.
So then,
And little time steps are always moving.
yeah.
There we go. Okay, how about somebody else? Will, what do you notice?
Me? I mean,
Pardon?
like the graph is the frequency of the speeds, and then no, bruh,
Yo,
I have
turn
no
that on.
clue. I mean, it just seems that the graph changes with the dots. I mean, I don't really know.
That's exactly right. The graph is changing with the dots. Okay, and what's the axis, the x-axis?
Speed,
It's speed. So it's the speed of?
the particles,
Speed of the particles, good. And what kind of particles do those look like to you?
gas.
Yeah, and they look like gas because why?
Oh, it's oh,
Xavier, why do they look like gas to you?
like not. I know it's gas because it's just like not packed. And
It's because the dots are all moving around and they have a much larger space. Or
Yeah, so they're moving around and they travel a long distance. Like follow some of them. Are you surprised how long it takes before they bump into another one?
no.
No? But okay, let me ask you this about the distance it takes for one dot to bump into another one. Is the distance further between dots than it is for how long it takes one dot to hit another dot? Or are they the same distance? Do you understand the question? I tried to make it as unclear as possible.
Not really.
Okay, here's the question. There is a distance, right, between dots.
Yeah.
Okay, and sometimes it's a big distance, sometimes it's a little distance. Then there's a distance that a dot has to travel before it hits another dot. Like pick a dot and watch. Whoa, that one. Whoa, 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 whoa. You know, sometimes it goes a long distance, sometimes a shorter distance. Here's my question. Is the distance a dot has to travel before it hits another one the same distance as how far apart the dots are? Lucas?
Oh,
I think you're breaking up.
Am I breaking up? Do you guys hear me?
Now we can.
Thank you. Okay. So, Zach, what can you say about the distances between the dots and the distance a dot has to travel before it runs into another dot?
The distance depends on how compressed the particles are together.
Okay, which is longer? The distance between the dots or the distance a particle has to travel before it hits another dot?
Pardon?
Which is longer? Edgar, who's the other kid? I'll enroll him right now. I'll put him on the roll. Who is that guy? I bet he knows about the dots. Oh my gosh, he's so cute. Okay, so the distance between the dots is the distance between the dots. Edgar, I'm giving you extra credit for bringing an additional student into our class. Now we're talking. Okay, is the distance between the dots bigger or smaller than the distance a dot has to travel before it hits another dot?
The first one.
And what's the first one?
The distance between the dots.
So the distance between the dots is bigger
Yes.
than the distance a dot has to travel.
The distance of dot that it travels is greater.
That's right. And that's what's called the mean free path. The distance a dot has to travel before it hits another dot is called the mean free path. And so in gases, the mean free path, like the example I give later is a study they did on nitrogen gas at room temperature and or at 0 degrees, I think, at 0 degrees and at atmospheric pressure. And the distance it had to travel before it hit another gas particle was 93 nanometers, okay? If you were in water, liquid water, the distance one water molecule travels before it hits another one is 1.77 angstroms. So 93 nanometers to 1.77 angstroms, that's a difference of 516. So gases travel a lot, they travel a lot further. Okay, now let's get to what a time step is. So this is a probability graph showing the different velocities that these gas particles fall at. And they're called time steps because they can't just tell us one speed. The probability of finding a gas at one particular speed is 0. But if you make it a little bit bigger and say, okay, what if a gas was going, 1 times or 100 meters per second, or another gas was going 500 meters per second, you couldn't tell enough. But if you said, what if it was going 100 to 110 meters per second? Or what if it was going 500 to 510 meters per second? Do you understand? So that's what a time step is. It gives us a little range that those gas molecules are moving in. Okay, does anybody find anything interesting about that graph? Or are you saying, why the hell are we looking at a graph about these particles? Any questions about this?
I have a question.
Okay, thank you.
Why is it all the way to the left? Why wouldn't it be like to the right? Like
why is it all the way to the left, the graph?
Because that's the speed of it. See, if you look down below, there's speed. So that's why it's all the way to the left.
What does that mean? Why is it all the way to the left?
He's asking why, like it's because of the speed. If you look down below the graph.
Well, it says that some molecules, it starts at 0. Are there molecules that are going like 0?
When the time step is probably at 0.
There are some little molecules that if you watch them, they're just kind of like, they don't really move around too much. They're just kind of sitting there. Can you find any of those? The ones that aren't moving that much? Okay, so the question is, why doesn't it go all the way to 7? Is that your question?
Yeah.
Okay, that is an excellent question. Oh my God. Okay. Because that's the way the molecules are moving right now. What do you think would have to happen to get those molecules to move all the way over at 7? What do you think we'd have to do?
Temperature change.
And so what kind of temperature change would that require?
Probably heating it up because the more heat speeds up molecules, so probably go to 7 if you heat it up, maybe.
So if we heated up the molecules, some of them would get to be 7. Would there still be some that are at 0?
Maybe. Probably not though.
There would still be some at 0. So that's what this graph is showing us, that when you have a large collection of molecules, then those molecules are going to move at different speeds. And what is the highest point of the graph telling us? The highest point.
Like the frequency or the speed?
So this right here, what does the highest point tell us there?
Probably 0.7.
Okay, but what does it tell us?
It tells us how frequent the particles go up to go in like 1.5 speed, maybe.
That is what it says. So what does that mean? Cameron, what does that mean, how frequent they are?
The highest point, isn't that the most frequent speed it's going?
And what does that mean, the most frequent? Use a different word.
It occurs the most.
So it's the greatest probability.
Yep.
That's right. The highest point would be where, if you were to pick some molecules, most of them would be going that speed. Is that also the average speed? Is the most probable the average speed?
No.
Who said no?
Cameron.
You said no, Cameron? Why would it not be why is the most probable not the average speed?
Because there's obviously other speeds on the graph.
There are other speeds on the graph. Is the graph symmetrical?
Nope.
No. So where are there more speeds, to the left or to the right of the highest point on the graph?
To the right.
To the right. So what do you think about the average velocity then of the particles? Is the average velocity higher than the most probable or lower?
Higher.
Higher. Oh my gosh. You know all the answers. Okay, here we go. Okay, so in like I said, they're trying to rationalize what these properties are. So that's what we did. We took a bulk property like boiling point. We made a graph of it. And then after watching a couple of videos, I tried to get you in document 1 to say, hey, why is the graph different for different molecules? Like the bigger the molecule, what happened to its boiling point? The larger the molecule, do you remember your graph at all? It's okay. Here's a graph similar to the one you drew. What can you tell me about as the number of carbons increase? As the molecule gets bigger, what happens to the boiling point?
Increases.
It increases. Okay? So that was one lesson. But the second lesson had to do with why are the cycloalkanes, why do they have a higher boiling point than do the just the regular alkanes? So I was trying to get you to think about how the structure of the molecule influences its boiling point. Okay? So today, though, we're talking more about just what is a solid and what is a gas and that sort of thing. So we're looking at the velocities. Okay. Does this graph look similar to the one that we just looked at?
Yeah.
This one right here? Doesn't that look like that graph?
Yes.
Okay. So this is called a Maxwell-Boltzmann distribution. This is a statistical distribution that's used a lot in science to explain various things. Okay, who among you can tell me why does this graph change when we have different molecules? So all of these molecules, and over here is the distribution or the frequency. So they call it a density, but it's the same thing. It's the probability of finding that molecule at that speed. So why does this graph change for each of those molecules? Which one is the narrowest? Which molecule is the narrowest?
The CO2.
CO2. And what does the 44 on the CO2 mean?
The MS -1.
So what is the 44 here? 44 is what? Okay. Pretty good. Hey, you answered a couple of questions. That's great. Anybody got any ideas what the 44, the 32, the 28, and the 18 are?
The volume?
Atomic mass.
The volume,
Atomic
not the
mass.
volume. Jaden,
Atomic
what
mass.
about you?
What?
Yeah, what do you think the 44, the 32, and the 28 are? And the 18? What is 18 with water? 18.
Well, obviously the lower ones are lower numbers, like the lower lines on the graph. So
Wait, oh, so this one is lower, so that's water, and this one's higher, so that's carbon dioxide. Okay, that's right. So what is the 44, the 32, the 28, and the 18?
maybe it has something to do with their boiling point.
No,
No? Okay.
that was a good guess.
Yeah.
Frank, you got any ideas? You sit right by the periodic table, Frank. What's on the periodic table that would add up to 44, 32, 18, 28, or 18?
Like the electron number?
Okay, could be the electron number, but in fact, it's the mass number. So oxygen
What'd I
is
say?
15, hydrogen is 1. So 2 hydrogens plus 1 oxygen is going to weigh how much?
18.
18. Nitrogen is 14. 2 nitrogens is going to weigh?
28.
Oxygen is 16. 2 oxygens is going to weigh?
32.
And carbon dioxide. The carbon is 12. Each oxygen is 16. So 32 plus 12 is?
44.
So what does this say about fat and skinny molecules, this graph?
The heavier ones.
The heavier ones, right here, the heavier ones are more on, somebody asked this already. They're more on which side of the graph?
The left.
They're more on the left. Where are the slower speeds?
The right. I mean, wait. The left.
The left. The slow speeds are on the left. And the light ones are on the?
Right.
The light ones are on the right. So what does that tell you? The fat ones move?
Faster. No, slower.
The fat ones move slow. The light ones move?
Fast.
Fast. Okay, and that's basically what that graph is showing us. That the heavy molecules move slowly and the light molecules move fast.
Is it like
Now,
the more complex?
Pardon?
Is it the more complex molecules move slower?
If you mean by complex that they have more atoms, that would be true because they have more mass. So if a molecule has more mass, then it's going to move slower. Okay? Now, that explains why the kind of shift to the right. But how come their heights go down? How come this one is tall and then it gets shorter there?
Because there's more distribution of speed.
There's a greater distribution of speed when the particle is light than there is when the particle is fat. You are absolutely right. Okay? Why?
Maybe because there's like more combinations of the different types of molecules.
Well, the reason is that, and once you take calculus, you'll learn how to do this. But in calculus, you learn how to take the area underneath these curves. So the area underneath these curves accounts for how many particles there are. And in this example, there are as many water molecules as there are carbon dioxide as there are oxygen. So they all have the same amount of particles. It's a comparison of the exact same quantity. Okay? So this is the exact same quantity. The carbon dioxide has the exact same quantity as the water. Okay? And that's why as it gets broader, it goes down because you still have the same amount. We have to have the same amount under each curve. Are you following that?
Yeah.
So when they first made these distributions, they did it just totally by calculation. So they had calculations and they had some ideas they were thinking about how particles would have to move and what the distribution would. So the whole thing is a mathematical exercise. And they spent pretty much a decade going through all the math, considering how particles would have to move in a gas and that sort of thing. Then they spent the 70s, or at least the Scottish guy Maxwell did. He spent the 1870s trying to test out this principle and to see if he could come up with empirical evidence that what they were saying theoretically was true. Okay? And nowadays, we have information like this because they take sonar, they take sound waves, and they take slow light waves, and they strobe those through gases and through liquids and even through solids. And they can actually, by changing the frequency of the wave, how much it vibrates, by changing that vibration, they can actually determine empirically each one of those time steps that you were looking at. So they actually have a lot of information to show that these statistical distributions are in fact what happens in real life. Okay? Okay, so now how does this graph differ from the one we were just looking at? We have 4 different graphs, and those kind of look like the ones we were looking at. But what's different about this one? Do we have 4 different materials here?
Yeah.
Oh, or
Exactly. How many materials do we have here? Hold up your fingers. That's right. We have 1 material, Leo. You are so right. There's 1 material. But what are the differences with this 1 material? Matt, Honig, we can't even see you, brother. Anyway, we have 4 different materials. So we have 1 material, and what's different about this material? It's at 4, Lucas?
Kelvin.
It's at 4. What are these?
For temperatures?
It's at 4 different temperatures. So now we're looking at a graph of just nitrogen molecules. That's the biggest component of air. Air is almost 80% nitrogen. So these are nitrogen molecules at 4 different temperatures. Okay? And so at 1200 K, what do you notice about the nitrogen molecules? They move on average, they're going to move the fastest. And the ones at 300 K, so that's about room temperature, 300 K, that's about 25 degrees, right? They're going to move the slowest. Right on. Okay. So that's what that's telling us. And why when it moves slower, is the probability of finding it higher? Why is this higher than, why is that peak higher than this peak? Orestes, what would be the reason that this peak is higher than this peak?
There's more pressure.
Well, in fact, it has to do with the fact that we have the same amount of nitrogen molecules at 300 as we have at 600, as we have at 900, as we have at 1200. So the area underneath each of these graphs is equivalent. But since this one moves slower, what happens to my graph if it moves slower? If I'm going to put it all here, what's going to happen to the graph? The peak is going to get higher. And if I spread it out, what's going to happen to our peak?
It's gonna decrease.
That's right. So, so the probability of finding any one, what do we call it, timestamp or here would be a speed step, is going to decrease as the gas moves quicker. Okay, and this is, what do we call this? We call this a speed step. So this is the area under the graph represents all the particles that move between this speed range. That looks like 1400 to 1625 or something. Are you following that?
Yes.
Or maybe it's 1300 to 1600. Maybe it's exactly what it says here. 1300 to 1600. Okay. Okay. So what do we mean by the probability density or the frequency of speed in this Boltzmann distribution? What do we mean by that? The ones in this speed stamp, do they have more probability than if we took a little speed stamp right here? We took these three boxes. Which has the greater probability of happening? These three, we made a little column out of these three versus these. Which has the greater probability?
The second one.
Yeah, the column.
What?
Second option.
This one right here, right?
The red.
So that's what, so the probability density has to do with, this one is more probable. If I were to stop, if I were to go out there and say, hey, you gas molecules, come here. I would find more gas molecules that were going between 1300 and 1600 meters per second than I would find those going, how fast do you think 1300 meters per second is?
1300 meters per second.
How many? 1300 meters per second
Like
in miles per hour. So it's moving 2,900 miles an hour. It's a pretty quick little gas particle, don't you think? Very hard to get a reaction out of you guys. Okay. We got to move on. We're running out of time. What is this graph showing us? Who hasn't talked yet? Matt Honig, what is this graph showing us?
On the left, it is a smaller percentage than the right. and
That's exactly what it shows. So, and this point right here is what? That is the point that is
the most probable.
the most probable. So on the right, the faster ones, there are more particles that are going to be faster than the most probable. So what does that say about our average speed? Our average speed is always going to be faster than
The average.
It's always going to be faster than the most probable. Things are always going to move quicker than the most probable. Are you following that?
Yes.
Okay. So you can explain this graph at 80K versus 300K?
Yeah.
So everybody understands kind of the way the distribution works? And this one is showing what? What is this one showing?
Bunch of different temperatures.
A bunch of different temperatures. And so it doesn't surprise you that the distribution gets broader and lower as the temperature gets higher, right?
Yeah.
Okay. So here's my question. Why do we need these graphs? Why do we have to learn about the Maxwell-Boltzmann distribution? How does that help us? Damn right. I'm going to a different screen. Are you with me?
Yep.
You sure you're not asleep?
Pretty sure.
Okay. Did that come up?
Yep.
No.
Did
We're
it
back
ever?
at the same screen. What happened? Stop sharing. Okay, share screen. And I want this one right here. It's not coming up for me. Is it coming up for you?
All I see is the stuff on top of like the PowerPoint. Like the
Okay, I don't even see the PowerPoint. Oh, wait a minute. Here we go. Do you see it now?
yeah.
Okay. Okay, so let's look at this. So the reason why we use a Boltzmann distribution is because we're trying to understand what is happening with the molecules just by looking at their temperature. Do you understand that? So we're trying to understand how their molecular mass affects the boiling point, how their molecular structure, whether they're a long chain, a cyclo, a branch chain, whether they're small, whether they're large. Okay? We're trying to understand how their intermolecular force would affect the boiling point. Are they polar or non-polar molecules? Do they have hydrogen bonding? Are there dispersion forces? We're trying to understand what role external pressure plays in the boiling point. We're trying to look at what role the space in between the molecules are. That, the gas molecules are going to go 500 times as far before they hit before they collide with another particle than are liquid molecules, okay? And the reason we care about this is because we say things. We say that the speed of the molecule determines the temperature. So what if we have a gas? What if we have a gas that is at 25 degrees? Do the water molecules at 25 degrees move as fast as the gas molecules at 25 degrees? That's right. Reject, 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 reject.
Who keeps playing Flight?
I don't know, man. But that's one of my favorite songs. Okay.
Can I get heat check?
What are they saying? Heat check?
Yeah, heat check.
I thought it was reject.
Nah.
See how little I know. Okay. But anyway, so you have all these different things. Are the molecules warming or are they cooling? Are they gaining energy in evaporation or are they losing energy in condensation? Then there are, there's a billion, quadrillion molecules even in a small, of course you can. There are a billion molecules even in a small droplet, a billion, quadrillion molecules. There are so many. So we're trying to characterize what's happening with these things that are so numerous we can't even count them. And that's why we have to use statistics. Are you following that?
Yeah.
Okay. So what about using, I wish I could make this bigger. Just a second. That's as big as, this little button won't work for some reason. But anyway, okay. What about COVID-19? So how does, this is a very complex thing, how a virus works. A virus is, compared to human beings, a virus is like a molecule size. It's really, really tiny. And they require a host cell. They have to get in you to replicate. They have to stick on to one of your cells. They have to break open that cell, and they have to inject their RNA into your cell. Then they have to get your cell to then build a protein off of their RNA, right?
Mm-hmm.
And so then once it makes that, then they have to get your cell to make like a little bubble on the size of it, and then that breaks up and it spews out new little virins all over your body, kills your cell, right? And then when it's replicating, when the RNA is replicating the new protein for the new little viruses that one cell is going to make, oh my gosh, all sorts of things happen. Sometimes it hangs on to the 5' side of the RNA, and sometimes to the 3'. Sometimes it makes little proteins. Sometimes it makes big proteins. So all these different things are going on, right? Is it complicated? Am I proving to you that how viral replication is a really big deal? Very complicated?
Yes.
Okay. So if you try to explain that to everybody, how helpful is that? So we need, in order to understand, because what we're really trying to do is stay alive, we need to look at a Boltzmann distribution for this thing. So let's go to a Boltzmann distribution. Okay. And I think we're here. And we're going to go to this. Okay, are you ready? But I think it's going to be hard to hear. You might have to play this yourself.
Probably turn on subtitles too.
What?
You can probably turn on subtitles if we can't hear it. We can
Okay.
just read it.
So let me.
Okay,
Check.
I think I've seen this video.
Run this thing. Okay, and then I'm going to turn this one down. Okay, and then I'm going to take off the mic. Okay, you think the closed captioning's on? Let's give it a try.
Bro. Oh my. Keeps doing that. Hella laggy.
Yeah, bro, same.
This still look like the bootleg John Green.
John Green.
What would you call that graph?
Frequency graph.
A Maxwell Boltzmann distribution graph.
Exactly.
Damn
Okay, and then
right.
what are our axes? We have the probability of the number of cases on the one side and what's on the bottom.
I can't read. It's like
Since outbreak.
Time
since
since
the outbreak.
So it's how much time it takes for to show the outbreak, right? Exactly what he was talking about. First, we don't know anybody who's sick. Then we know a lot of people who are sick.
Damn right.
Okay. So how do we get the broader one?
More time.
That's right. It just we make sure that the pandemic moves slower, right? So this is counterintuitive from the one we just saw. That had to do with faster speeds. This has to do with making sure that the outbreak is slower. That lowers the probability that anybody has it, right?
Yes, sir.
Oh my god.
Bro, this is class.
I need a bad bitch. That's right. It's exactly what the science of epidemics tells us. Oh, that is so annoying.
Okay, you following the lily pad analogy?
Bus is over.
Okay, it is just about over.
Wait, is it end at 11? Or?
The lily pad analogy.
Okay, let's have a guess. How long is it going to take for the pond to be covered halfway if it takes 60 days to cover the whole pond?
30 days.
30 days.
30 days?
5 days.
15.
15?
Week.
I say
wait.
3.
No, like 56.
Like
Yeah, like
59.
Got it.
You're wrong.
7.5.
What?
8.5 days. No, 7.5 days. 7.5 days.
I said
The
59.
games?
So the last day it doubles. That's what exponential growth is about.
Oh my god.
Matt.
Frigga.
Okay. There's the new question. On what day do the lily pads cover a mere 1% of the pond?
Day 5.
Day 5?
I said day 50, 57.
Monday.
Day 57?
day 30.
1.
Primo actually is very close to the answer.
58. Day 58.
68.
Oh, 54.
1% at 54.
Damn.
The whole pond covered on day 60. So the last 10% of the time gives you 99% of the cases. That's why you have to have some understanding about these changes.
So we just stop it before that last 10%.
Okay, I think class is over. Thank you very much. I appreciate it. Do
Pats,
some work and get it into
Pats,
me.
Pats.
It's good to see you.
Hey, with the cash, like an exo chain.
Pardon? Okay. Ci vediamo. Moted.
Oh,
That's my
ciao.
word, man.
Au revoir, Mr. Patterson.
Okay.
Hey, I'll catch you soon. Deuces.
Ciao.